Hello, welcome back. We are in the third discussion on Chapter 5 on predictive coding. We will have one more discussion on Friday with Fraser on Chapter 5, and then that will conclude the Part 1 chapters. And then we'll take next week to review Part 1, look at the questions that have been asked on the introduction and up through Chapter 5, make sure they've all been addressed, talk about any other random questions, look a little bit more at the code, look at any other uh, topics that people want to explore related to the first part of the book, and then we'll jump into part two. Let's today pick up with just looking at the concept map and starting with, is there any specific area or a question that somebody submitted before that they want to start with or bring up right now related to chapter 5? Okay, so we looked at the concept map previously, and we'll probably return to it. And I'll also just bring up this is the chapter 5. This is the fundamentals open source code repo. And I just made a couple updates to the chapter 5 code. So all the methods are in here in SRC modules. They're all tested and documented using core methods across the different chapters, so you can see a little bit more continuity there. And they're used in this chapter specific fashion. So if there's another type of figure or another animation that you'd want to explore, just make the request in a group meeting or through any other way. Okay, we have some questions already on chapter 5. And last time we basically got to, I believe, the maybe the end of section 5.1. I don't exactly remember. But just, is there in the chat or raising their hand? Is there anything that somebody wants to start with first? Or just any random takes or impressions that people got from reading chapter 5? Or any overview or update on how does predictive coding relate to active inference? Okay. All right. Um, well, there's a lot of ways to continue about this. Let's briefly look at what's going to happen in section 5.3 and 5.4 as extensions, and then return to 5.2 to bring us back to the core kind of Lego block of predictive coding. Because it's good to know how these extensions go, and it's easier to take that jump to extensions when you're familiar with what the core method is. So again, to recall, in section 5.1 and 5.2, we basically get all of these core mechanics in terms of how do sum of squares, sum of precision weighted squared prediction errors, that's what we talked a lot about last time, relate to mean-based updating of the variational posterior, and that's simple predictive coding. Now let's peek ahead to the two extensions, the multivariate case in 5.3 and the hierarchical case in 5.4. Then return to 5.2 to the core, and then we'll see if the questions have been addressed and if we want to write any responses there, or if there's any other questions we want to add, and then just you can add to the questions table if you have an uncertainty, including I don't even know what to ask, which there's definitely pages where that hits pretty hard. All right, so 5.3, multivariate predictive coding. So in the page 114, Sanjeev writes, the model we have investigated so far is very limiting because most of the useful scenarios that we wish to model in the real world deal with multivariate data. So, for example, not just one thermometer, but you have a whole bunch of thermometers, or not just one EEG sensor, but you have 64 EEG sensors on Morgan's skull cap, or whatever it is there. That's one type of multivariate inference where you're dealing with observation or sensor channels, and there's a bunch of them that are like spatially distributed or have other different attributes within a modality, like 64 thermometers. Or you can have the multivariate situation where the modalities are just totally disparate, like temperature and humidity, or it's EEG and color. Um, Second paragraph there. The generative model now consists of a vector of hidden states. And that's basically the move that this section is going to trace, is just going from a scalar, single number, to a vector, and then just continuing on analogically with extending all of these calculations into the vector setting, not just the scalar setting. Cobus?
Daniel, just because you're at that point, X star element of RC, that should probably just be X, not X star.
Good point. X star would imply that it's the generative process consists of those X star true values. Good call. Thank you. 5. This is how to add errata, by the way. If you ever find any typo, please just add it yourself.
And then in just the very next sentence, vector value function G underscore M, and in parens X, that X should probably be a bold X.
Yeah. Should be regular. Yeah, good opportunity to revisit. X star should be X star is the real generative process external state, but the generative model just uses X to represent its estimate of the latent state. That second one I'll let you or someone else add. Okay, thank you for that. So the move here is just to vectorize latent states and or vectorize observations. In general, with state space models, this book is going to take the approach where we start with like one observation, one latent state, and then we'll get to one action. In general, you could have any number of observations, any number of latent states in the generative model, any number of actuators. So you could have like one observation getting unpacked into many latent states, belief updating, or vice versa. You could have many observation channels mapping to a reduced number of latent states. So those are just kind of the anatomy or the morphology of these different state space models. Um, Example 5.5 on page 115 is going to be a two-dimensional grid example. So here, those two dimensions are, that's where X star is used correctly. The external states of the environment are indicated by the vector X star. Is within, that's the fancy sideways E, big R, fancy R to the second power. So real numbers, and there's two dimensions to that real number vector. like 0.5 comma 2.5 is the true location of the food in this example. And the M sub x 1 1 is the agent's belief. That's on the generative model side, on the agent side. So that's an example where um, both of the latent dimensions are spatial. And then later down the page, the observed data, so there's also two dimensions to the observation data, can be interpreted as two different types of sensory modality, such as arbitrary units of olfactory perception and light intensity. Um, so that's the sort of cheese discovery example of two-dimensional predictive coding. Um, in example 5.6, there's the parameterized multivariate predictive coding model, and that big bold theta, the mixing matrix, does a lot of the work in uh, hinging variables that have different shapes because the mixing matrix can be kind of like wide and shallow, or it could be very tall and narrow, and that mediates. It's kind of like an experimental design matrix mapping from whatever dimensionality of observations you have to latent states. And that example is on in equation 5.27 is 2 wide and 4 tall. So that's like mapping between a 2 and a 4 dimensional state space. And we can see from figure 514, we have two true x values. And then mu sub x is the mu is just a it's just Greek for mean. It's the mean central tendency of those x estimates. It'd be nice if they were like numbered, like sub one or sub something. Um, and this is showing how, as a function of iterations, which is to say, like those gradient descent, gradient following iterations on the variational free energy landscape, those two estimates of latent states are getting updated, and then they hit this stationarity pretty fast. And then there's four input channels. And so here's the overall variational free energy dropping. Um, and I wonder if that should be 1, 2, 300, or if that's denominated differently, it's not reflected as that way. But we can look at equation 527 and see how it's 2 wide and 4 tall, and then connect that to how there's two latent states here and four observations. So that mixing matrix, which is kind of like the likelihood matrix overall, is mapping from any number of input channels to any number of latent state variables. Okay, any thoughts or questions on this multivariate case? Again, it's the intuition that is built in that single dimensional, single sensor, single latent state is going to carry forth like pretty cleanly into the multivariate case. And then again, we haven't dealt yet with action, but we will in the next chapter. And next, I think one or two chapters. And action is going to get tucked really nicely into the way we've been talking about latent state updates. It's just a latent state that is under the agency of the generative model. Okay, now quick peep into section 5.4 on the hierarchical predictive coding. Okay, so Sanjeev writes, hierarchical models are a useful way to represent more complex features in the world that have hierarchical structure. For example, a face or a tree. And this section will introduce the concept of hierarchical model, which will be investigated in more detail in chapter 8. We can capture the hierarchical nature of the world by extending the predictive coding model discussed in the chapter by introducing empirical priors the hallmark of hierarchical Bayesian modeling strategy referred to as parametric empirical Bayes. And what PEM is going to do is in addressing that question, like, but how do we pick our prior? The answer of PEM is, well, take your observations and then use the summary statistics of your observations or a batch of your observations or bootstrap or resample or some other way to use the data you have to set a prior regarding itself, essentially. Make it likely to have been seen. So it's almost a quasi-frequentist approach because it sets what could be a maximum likelihood prior in a way that initially, if you only had that, would be a bit like circular and self-descriptive. However, for going out of sample, then you have this empirically derived prior rather than a priori or like axiomatically set prior based on the data that you have. Okay, so we see the generative model in equation 529, and it is going to be reflected in figure 515. So here we have a latent state that is going to have an estimator for the mean value of the latent state and the variance of the latent state. And it is going to have a variational family that's normal, a Gaussian distribution, which is going to pull variables x with mean and variance m sub x s squared sub x. So we have a Gaussian prior on a latent state x. Then there's this causal direction arrow where x is going to emit observations y, which are shaded in gray. Observations are going to be parameterized by two features. They're going to be parameterized by this g sub m mu of x, which is the generating function in taking mu of x. So that is basically the mapping between latent state point estimates of central tendency and the emitted observation, and a sigma squared sub y, like observation noise as parameterized. And then observations are going to be parameterized by another normal distribution that's going to give us y observations according to the g sub m of mu of x central tendency with sigma squared sub y variance. Mark?
Yeah, I'm going to reveal my behindness just a little bit here, but then asking about that variable at the bottom that I think you have that could be seen as the likelihood, correct? That the term at the bottom you just described, or it's the observation. But I'm wondering if that notation there is as described, if it reflects a likelihood in that it's y, the observation, conditioned on. I know the notation doesn't suggest that, but could you say it's conditioned on the mu of x in that way? Or am I just reading that wrong?
Yeah, yeah, you said it correctly, which is we don't see a vertical line, the pipe. So it's not that
Right.
it's conditioned on anything, but yes, does it depend on like what does it how do you get a y? Well, you get it from the g sub m of mu.
Mhm.
That's going to give us the point estimate of the central tendency of our expected y given a mean of the latent state, and it depends on the um variance, sensor noise. So yeah, could you say it's conditioned upon those two? Yeah, basically. It depends on
More
them.
technically, it's parameterized by, is
Yeah.
that
You could
okay?
say it's parameterized by those two variables, or it's
Uh,
conditioned upon them, or it depends on them.
okay.
Sometimes conditioned is just using the vertical line,
Right.
like x given y. But yeah, like in the sense that changes in those variables influence their differences that make differences. it is, you could say it's parameterized, dependent or conditioned upon.
So could you characterize that as a likelihood then, or
You would
not
use the
quite?
parameterized distribution to
Uh-huh.
calculate a likelihood. And like
Okay.
a kind of intuition for why that matters is like, let's just say that it was the distribution was parameterized as like 10 plus or minus 5. Then 9 is not so unlikely. But if it was 10 plus or minus zero point zero 0.01, 9 is super unlikely. So the likelihood of an observation, given the parameterized distribution, is something you could talk about. But this is just stating it in a generic way.
Got it.
Uh,
Thank you so much.
on that point, I recall reading somewhere in this book, Sanjeev is very particular about keeping the semicolon distinct from the pipe. And I think he does mention that in general, people often use those two symbols interchangeably, but Sanjeev is very particular about keeping those apart. So the pipe is literally conditioned on, but the semicolon strictly means it's parameterized by the following symbols. And
Yep.
he uses that as subscripts often. So he's very exact about that.
Yep. Thank you. So this right here is like, this is the Drosophila. This is the minimal setting where we're looking at one latent state, one observation. We're seeing it graphically though here, with the mean and the variance estimates for each of them getting injected in, latent states emitting observations. And then the distributional notation on the side there. Like equation 5.29 are these two equations. So those are identical representations. The graph contains that information, except the n, and that's why 5.29, to Mark's point, the likelihood is the probability distribution of y given x. So like it, that's a true conditioned likelihood, whereas this is just being stated as like the equation. Okay. So that was like a little bit of a review of just latent states and observations where they both have separately parameterized normal distributions. Then we're going to add a third floor on the house in figure 516. So now, because we're talking about potentially multiple higher order layers, instead of calling the observations y, we're just going to index them as mu sub x at layer 0. But the name or the symbol of an equation doesn't matter. It just needs to be intrinsically coherent. And then we have mu sub x at layer 1, mu sub x at layer 2. So we know which language people speak when they index at 0 versus 1. You could call these layer 1, 2, and 3. You could call this one y, and the second one x1 and x2. But here we're just using the 0th layer as the ground floor. Then, if you just were to ignore the top, we would have exactly what we had previously. But rather than using like s squared for x's variance component and sigma squared for y's variance component, we're just going to have a consistent nomenclature with sigma squared to the index layer. Um, and we just add basically a prior on the prior. So it's just like adding the third floor is going to relate down to the second floor, analogously to how the second floor is going to relate down to the ground floor. And we see at each of these layers, we have a normal distribution where mu sub x at layer 0 observations are being generated by the distribution that's normal parameterized by the generating function from layers layer one's second story, point estimate, and the sigma square of 0, sensor noise at the ground floor. So that's how you make predictive models that are hierarchical. You just have another layer that supervenes upon or sets a higher order prior, and you can keep going. So it's not that there's a generic or even a situation specific answer of where the buck should stop, but the good news is you know for a given generative model where the buck does stop, and you can use principled methods like Bayesian model comparison, Bayesian model reduction, Bayes factor, all these different kinds of features to select the order of model that balances, for example, accuracy minus complexity by rewarding models that fit well and penalizing having extra parameters. Magdalena?
Yeah, so at this level of abstraction, Daniel, could you walk me through the generative model term? So at the level, at the ground level, you have the generative model with the 1, which refers to the next level. And then in the second level, you have generative model with 2, which refers to the third level. And at the third level, there's no generative model term. Why is that?
Yeah, it's kind of that is where the buck stops. It has that's why it has like a slightly different notation. Like great question though. Layer 1 and 2 are almost exactly structural. They are structurally identical. They're both going to look up to another Bayesian variable, another latent state, which they are an emitted observation of. So, like here at the observation layer, that shaded gray, we see that that is going to get drawn from the generating function and point estimate of the first latent state and its variance profile sigma squared of 0th index. Now, exactly analogously, layer 1, second story, is going to get drawn mu sub x of index 1 from a normal distribution parameterized by the generating function of the point estimate of the third story, second
Mm.
layer, and the noise component of first layer. Okay, so if we were going to go in the infinite recursion setting, then you just keep going with that. You just keep on bumping up those numbers by 1. But every building has a top story. So here is that top layer where it is just being parameterized in a slightly different way. That's that is where the buck stops for that. For example, let's just say that we have the observation of like we could think of this as a three-digit number. We have like the ones place, the twos place, or the tens place, and then the hundredths place. So just like a three-digit number. And so we're going to say, okay, we're going to be sampling from that ones position of the three-digit number. And it's going to have its own sensor noise and stuff, but also it's going to depend upon the state of the tens. And then in
Mhm.
that exact same way, the tens digit is going to have its own sensor noise, and it's going
Mm.
to depend upon the third position. And then the third position, you just say it's being drawn from a uniform, or it's being drawn from just the number 7, or
Okay.
it's being drawn from 50% of a 7 and 50% of a 5. So the top level prior has like a little bit of a different character because it is not generated observation like from another latent state.
What is a bit bothersome to me is equation 5.32 does not strictly align with what we're seeing here.
Okay.
Uh,
So,
yeah, one last thing.
uh-huh.
Does the math, is there anything in the math that presupposes a temporal sequence, or is this a hierarchy that is independent of any temporal. This has to happen first, this second, this third.
Great question. This is actually not related to time.
Okay, thank
This
you.
could just be like it could be like, for example, like the three-digit number case doesn't have a temporality. Or it could be like we're talking about
Yes,
country, county, and city. So it could just
right,
be like instantaneous spatial. But
got it.
yes, you might fit it to time series data. Okay, Cobus, yeah, great point. For example, the 531 uses Y for the first layer, right? Is that what you're referring to?
Um, yeah, I wasn't really studying the relationship between 531 and 532, but I just noticed 532, the index on the left-hand side is different from the index on the first term on the right-hand side, and that is not the case in this
Yeah,
graph.
yeah, good point. We'll note this and someone could add it to errata or we'll revisit it. But in 531, my concern or question is that the first layer is given with Y as the observation, and then the first layer is Y conditioned upon mu sub X layer one. So that basically says that so either Y is equivalent to mu sub X of zero, and it's just mislabeled, or you would need another edge from the zeroth layer to Y, which seems a little bit less probable. And then the second question is that you just raised there on 532, Cobus, is we have prediction error epsilon. So we have epsilon layer little l, which is here indexed to zero, equals mu sub x of l minus one. But that would be negative one if l were zero. So that is an inconsistency as well. Um, Regardless, in spirit, accurate, but this is like why um why it, without going too much into this, why it's important to have like multi-witness rendering of manuscripts where the LaTeX plain text math is type checked against the simulation and possibly even a theorem proving environment because and there's a glossary with an ontological lookup table because it's really, really easy to have variables be referenced multiple ways or to lose track of indexing. Where we get with that though is again staying with this notion where the lowest layer is mu sub x of zero, even though it's kind of a little bit called y. Um, we get descending predictions and ascending prediction errors, which are not shown on this on that Bayes graph. But if we remember back to how do you set those priors with a parametric empirical Bayes, that's basically like what is happening with the prediction going down. But again, that's just a spatial association. That's you could have it left to right or whatever. And then coming up is empiricism. So it's like idealism and empiricism meeting in the middle, pragmatism, and slightly updating. But you could set it so that the mu sub x layer one never updates. It just relentlessly issues the same prediction. Or you could have a lightweight mu a layer one that just simply updates to the empirical layer zero. That is the question of attention. Okay, Mark, could you say each level constitutes a mini generative model and that those three are a chain of generative models, but referred to as the hierarchical generative model? Basically, like if you just imagined that you just had one variable by itself, like we're just talking about a temperature in the room that just has a mean and a variance. So kind of like the simplest statistical variable, or even simpler, like a single parameter model, like a Poisson distribution, like a waiting time for a bus. It's just like parameterized by 20. Um, then you could have like a hierarchical model that's composed of that, and that's kind of the power and the excitement of graphical modeling, that this is like the Lego environment where you can compose generative models of arbitrary structure and state space composition. And then you can do local free energy based minimization with message passing. And with those local update rules, that would compose nicely and accurately into equation 534, which is like the net free energy. Like if you were to account for all of the belief updating and variational free energies of each node, you could sum them without remainder. There wouldn't be like another component to incorporate. So that is the idea, and this is the basic motif. We have observable variables and unobserved variables. And so those are the two kinds of statistical variables. You got inside and outside. Those are the two kinds of variables. And then you can compose the situation where you have 500 latent states that all cause down to one observation, like 500 medical factors, and is this person going to survive or not? Or you could have one latent state, like do they have a disease or not? And then it could have 500 biometrics. So like you can compose within that environment whatever state space of model you want. And then you wrote, are predictions priors? Basically, yes. The prior is like prior to finding out, what did you expect would happen? So that's why it's prior to the observation. And then the posterior, updated belief after the observation becomes the prior belief for the next observation. Um, and so we can look at that in the graphics in the code base. So we can like see, okay, here's and here in this version, I did assume slash hypothesize slash infer that mu0 is y, just to be clear. So here's like the observation is clamped to 2. And then the beliefs are updating at these other layers to minimize the per layer and the total free energy, given that clamped observation.
Nice.
Yeah. And 5.4. Yeah. Example 5.4. That this is just a slightly this is a not example 5.4 or it might be example 5.7, but I'm just using like a little older PDF version a little bit. Yeah, similar. Okay, and then section 5.5 gets to the summary and conclusion. So let's just look at those kind of that the bathtub style, beginning and the end of the paragraphs. In this chapter, we introduced a very simple implementation of predictive coding as introduced in Frist in 2005. The model introduced the notion of prediction errors, which act as a feedback signal in the brain. If observations are accordant with expectations, don't change. Change to some proportional extent and in the direction of whatever the prediction error or discrepancy is. Absolutely, transformed into surprise, or bounded by a variational free energy. Since the prediction errors are a measure of uncertainty, when we minimize VFE, we engage in the process of reducing uncertainty in our model, which is just the complement of maximizing evidence in the model. If I would have had what I if I would have known and integrated what I know now, I would have been less surprised by the observation that just came in. If I would have known then what I know now, I would have had a better fitting model Ergo, I would have been less surprised by the evidence coming in. We began with the E form of the VFE, dot, 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 dot. Some simplifications were made, some rearrangements were made, and that revealed a gradient descent rule that could be used to estimate values over iterations of variational inference. Importantly, the iterations of variational inference are not necessarily the discrete time steps. That's why we see like dozens of iterations. But that could be happening within one time step. And that's something that, like, if you play with RxInfer, you can explore. Is like, how many gradient descent iterations do I have the budget for, or am I going to um, dictate must be done within a given time click? Um, Third paragraph there. The model has clear connections to variational inference, but the formulation presented here is different than the original predictive coding paper, which was the Rao and Ballard 1999, which we recall from last week. It doesn't go into the variational side. The predictive coding perspective presented here is useful because it demonstrates under assumptions about the density, free energy minimization is a way of reducing uncertainty. Then, um, predictive coding has roots in the study of ganglion cells. So going back to the 50s, some neuroscience citations, you can just look at the years there. 57, 80s, 50s, 60s, and that led to the 1999 Rao and Ballard work. And this notion of predictive error minimization is related to a long line of research in neuroscience, reviewed by that 2012 paper. And finally, action has been recently added to predictive coding models producing active predictive coding. That is the same Rao in the 2023, which is kind of like a convergent cousin of active inference. And then that last section, predictive coding developed alongside a number of Bayesian methods that have been applied to the brain, which collectively, loosely, is the Bayesian brain hypothesis, referring to different aspects of like predictive coding, predictive processing, the pragmatic turn, all these different features, probably approximately correct or PAC computing, and um, Pizzulo et al. 2024 described the way in which many historical antecedents to active inference unite to form a single computational theory. Active inference is not about the brain. It's more of a systems science method that is able to be used to describe the brain and kind of continues to yes and all of these like what ifs and alternative systems, leading to the ability to specify active inference generative models that recapitulate or encompass or extends variational approaches to, for example, visual physiology. Okay, so we could return to some of the questions and let's just see if there's any questions to address now. Okay. Maximum entropy principle. So, more entropy is more choices or degrees of freedom. Is this more options to learn? And Andrew wrote, yes, the initial distribution we use for making our inference in principle should be high entropy. So you can read Andrew's response there. And I'll also bring in, this was live stream 57 with Thomas Parr on active data selection, talking about Bayesian clinical trials. And in this set of streams in this paper, they go into the best detail of what are the situations where epistemic value is equivalent to maximum entropy? What are the situations where epistemic value is different or better than maximum entropy-based sampling? So if that is something that someone is curious about, go into this active data selection information seeking paper, which has good discussion of the maximum entropy, which is why I'll just leave it at that. Okay, page 118. Is there any intuitive reason why we define G sub m equals 0 for the top layer so that the prediction error simply becomes the mean of the prior? Now, this is stated almost as a definition. I wonder if there's a more principled motivation for it. Yeah, the short answer is like the buck has to stop somewhere. You have to have some top level of the building with a roof. You have to have some top level variable that's just going to be like, it's just this number, or it's just drawn from this distribution. And then you could make another higher order variable and make that more complex than just stating it to be a certain number. But then that would just solve it for one layer and just move the next layer to be where the question was. Page 118, prediction error becomes equivalent to the current value of mu sub x. So at the top layer, the prediction error just becomes equal to the current value of mu sub x. Should that be m sub x instead of mu sub x?